Probably sounds good.
Michelle, did you write down the values? Or did you? Did you have the values of it? Is that what you got? That's not right.
I have the values.
Can I borrow your book for a second? Oh, okay. Sodium ions in there. Positive or negative? Are you still working? I'll wait.
Positive?
Small positive. Okay, not even in the hundreds. So positive delta H. That means if you were using baking soda in the freezer bag lab, when you started the reaction, you zip your bag closed and then you put the reactants together. What did you notice? Even if you didn't have it, now what would you have noticed now that you know what you know?
Be heated. Or got cold.
It's endothermia, it would feel cold.
Yeah.
Yep. You remember how someone felt hot and someone felt cold? Or maybe you didn't notice anything about the temperature. But some carbonates and acid are exo and some are endothermic. It's kind of cool. But this one is endothermic. The delta H that you get is positive 28.5. Yeah.
If you do like the reaction where it's like really cold, like or something like so.
Yes. As long as there is some energy in the surroundings, it would probably be a slower reaction because there's less energy available to it. You know, if you have this reaction and it's endothermic, if you run it at like the temperature of boiling water, it goes really fast. Room temperature, it goes fast, and in a freezer, it would go slow. So yeah, I mean, it depends on how much energy is around it.
Only one place faster than one, or no place faster than
You know what? That is true. Like in the number 240, did it have a decimal, or did it just that? Oh, that should have kept us. The answer should be 30, positive 30, because the last sig fig in this number is in the tens place. That means when we add and subtract, the last sig fig should be in the tens place in our answer.
Wait, what are we putting it in?
No, it's in the tens place. The 40. That 4 is the last sig fig in that one. So that means that goes up to the 10th place. Our answer's got to be, that's got to be the last sig fig in our answer. So 30 would be the correct number of sig figs. Another thing that people are real confused about, and I understand because it is confusing, is the unit. Is it kilojoules or is it kilojoules per mole? You know how in the table, these individual values are kilojoules per mole? Without realizing it, you were actually canceling out the moles because for each of these, you multiplied them by 1 mole. So this is 240 kilojoules per mole times 1 mole. So it really just winds up canceling the moles and giving kilojoules. In general, the delta H of a reaction is just in kilojoules. And the assumption is that's the energy for whatever coefficient is in each of these. Well,
Should you put a decimal point after the 0, otherwise it has like no sig figs at all for the hydrogen?
that would not count for sig figs.
Like if we had the number, it has 0 sig figs.
So it wouldn't count for sig figs. So if you're adding 0, it does not going to count.
We add
Okay,
0 to all these
now,
numbers.
I also have some other information about this reaction. Down here, these are 2 reactions that involve hydrogen and the bicarbonate ion. Could you use these 2 to find the delta H of that reaction, of the above reaction? Could you use these 2? What would you have to do to manipulate these so if you add them together you can find the delta H?
the console.
Yeah, it's actually quite simple. Once you kind of see what all is given to you there.
Yeah.
That first reaction, just turn that around.
And then
Change the sign
HCO
on.
would cancel.
Yeah, the HCO3s would cancel. Yep. So yeah, if we turn this thing around, it's positive 16.9 plus the 11.8. Now, does 16.9 plus 11.8 give you that number? Okay, so which one do you trust more?
Heat of formation.
Yeah, always trust the heat of formation table the most. Yeah. Now, why is that? Maybe these values were found experimentally. Of course, these
Yeah.
are too, and maybe they're average numbers. Yeah. Yep. Okay, so that was a pretty simple Hess's law problem, but you can see that it's used again. Take a look at number 3. Now, there are several problems in the assigned homework exercise that have to do with number 3, where you have stoichiometry and thermochemistry together.
You have to find the molar mass.
Yep.
Isn't it always, it was like always around 100 for the carbonate.
Carbonate itself is 62. You just have to add the hydrogen and the sodium to it. 62?
48 plus 12.
No, sorry, carbonate is 60. Carbonate is 60.
It's 101.
No. You're thinking potassium.
Oh,
84.
Yeah. Baking soda is 84.
Formation is required, energy required minus energy release, right?
So what's all numbers recommended?
Oh, from the bond
You
energy.
should do last
From when you use the bond energies,
Because you have.
it's the bond energies of the reactants minus the bond energies of the product.
That one, why was it positive? Was it?
For the heat of formation, take the total of these minus the total of these.
Why wouldn't you do left to right?
Because delta always means final minus initial. It's always the end value minus the beginning value. Ready? Put in kilojoules. Yeah. And it's already in kilojoules. What is the relationship between heat and moles? And that's what I mean by that is this. When you have 4.2 grams of sodium bicarbonate, 4.2 grams of NaHCO3,
Yeah.
first thing you do is convert it to moles. Anytime you have a quantity that's not in moles, it's probably going to be right to convert to moles. So as 1 mole of baking soda over 84.0 grams. That's baking soda. Okay, that gets to the moles. What is the relationship between moles of this and heat?
30 kilojoules.
What?
3 kilojoules per mole.
Oh, because you would think that. Here I'm stuck on 28.5. Yeah, we'll call this 30. It's 30 kilojoules for every 1 mole. Yep. Whatever the coefficient in front of this thing is, in this case it's a 1. However many of those coefficient of that equals that amount of energy. So it's going to be 30 kilojoules over 1 mole. That's it. 42 divided by 84 is about 1 over 20. 4.2, I mean. So 1/20th times 30 is around, what, 1.5 or so. Rounds to 2, because we only allowed 1 sig fig. Yep. So you can see this. Take a look at some of the exercises in the end of the chapter that have to do with this. In the 40s, now let's see. Number 46. On the very bottom of the page.
Yeah, let's do this one.
What's that? Oh man, they come up with it. Yeah. Some chapters have like 180 problems. Man, that's a lot. So anyway, number 46. So number 46, they were just getting going. How much heat is involved for the production of 1 mole of water liquid? So notice that the delta H is not in kilojoules per mole, it's just kilojoules. What that means is when 2 moles of this react with 1 mole of that, and it makes 2 moles of that, that's what the delta H is. So in part B, look at part B. If 4.03 grams of hydrogen are reacted, so you take that 4.3 grams, convert it to moles, and then multiply by negative 572 kilojoules over 2 moles of hydrogen. So you have that relationship there. Whatever the coefficient is related to whatever the delta H is. There are several problems like that. That's what they'll be doing. Just one other thing that I need to show you now. That will wrap it up for chapter 6. That's everything in chapter 6. We've done like Q equals MC delta T, conservation of energy, calorimetry, how to find delta H, Hess's law. There's one little topic that's in chapter 10 that has to do with energy that we should talk about. And whoops. And that has to do with, now temperature changes, we've already seen the Q equals MC delta T. Anytime a temperature change, you can find out how much heat is involved. But when you have a phase change in physical state, I believe, first hour, everybody in the room said that they had seen this before, so I'm going to trust that all the Chem 1 teachers do it. When you have a phase change, during that change, the temperature is not changing. If you have water boiling in a pot or in a beaker, and you stick a thermometer in there, as hot as you turn that heat source up, the temperature of the boiling water is constant. All the energy that's going into the boiling water is working on changing the physical state. It might boil faster, but the temperature stays constant. And the same thing is true for a block of melting ice. If you have melting ice and you've got a thermometer stuck frozen in the middle of a piece of melting ice, that ice will raise to 0 degrees, and then at 0 degrees, that temperature stays constant. At 0 degrees until all the solid has melted down to liquid. Sir?
There's this one thing called joules. Like there's this product called joules on like you can look it up online. Like I had to do this for like the online course. So they use this property to like cool down coffee really fast. Like they're like beads you put in your coffee and it cools down your coffee really fast. And it keeps it at that temperature for like a really long time, for like 5 or 6 hours. Using this property. By storing the heat inside a phase change, and then it keeps it there and then it releases it later. It's really interesting.
That is interesting.
Yeah.
I've never heard of that before. So it's like this tablet thing that you put in your coffee, and it cools it down.
Really fast.
And then it keeps it at a certain like drinkable temperature.
Yeah.
Never heard of it. So anytime you have a temperature change, you can use this to find how much heat is involved. But at the phase change temperatures, when the temperature's not changing, you can't use that because delta T is 0 during a phase change. So we have to use, for melting, we're going to use Q equals the heat of fusion times moles. Do you remember seeing that? Okay. And just so you have a definition, the heat of fusion is the amount of heat required to melt 1 mole of a solid. That's kind of like specific heat, but rather than using grams, it uses moles.